Hello everyone, I'm Qiao Zhang and I'm a first-year PhD student majoring in information science at Drexel University. Today, I'm presenting my most recent work on the project Investigating Knowledge Tracing Models Using Simulated Students. This is work done in collaboration with Christopher McLennan, my PhD advisor. I'd start off with a brief introduction of Intelligent Tutoring Systems, ITS. Intelligent tutoring systems are widely applied in K-12 education to help students to learn and master skills. In order to better focus practice, knowledge tracing algorithms are embedded in the tutors to keep track of what students know and do not know. Knowledge tracing models take labels of the skills needed to perform each step, which we call knowledge components, KCs for short, and students first attempt correctness to predict whether the students will correctly solve a new problem containing that KC. Many studies have proved the efficacy of such approaches in offline settings, but little work was done exploring their application in online settings. In this study, we filled this gap by running online simulated experiments to investigate a few knowledge tracing approaches. So, what is knowledge tracing and why is it important in designing an intelligent tutoring system? By definition, knowledge tracing is a task modeling students' knowledge over time so that we can accurately predict how students will perform on future interactions, usually by observing the correctness while doing exercises. There are multiple knowledge tracing approaches like Bayesian knowledge tracing, BKT, by Corbett and Anderson in 1994, 3 in a row, or the Strike model by Heffernan and Heffernan in 2014, and deep knowledge tracing by Peach and others in 2015. Both the BKT model and the DKT model have a few model parameters. For example, the BKT model has 4 parameters, denoted as P-know, P-learn, P-guess, and P-sleep. This graph demonstrates how BKT models student knowledge in a hidden Markov model as a latent variable, and the state is updated by observing the correctness of each student's interaction in which they apply the skill in a problem. Then, where do the initial model parameters come from? Will they affect the model performance? And how can we obtain these parameters? With those preliminary thoughts, we intend to answer 2 main questions. Firstly, can we run simulated experiments to get some data and generate the model parameters when we do not have human student data? Secondly, talking specifically about online knowledge tracing, what would be the best, or in other words, most appropriate knowledge tracing approach? From our observation in literatures, we noted that the model parameters were manually picked in some of the studies, while in other studies, the researchers ran a pilot study to first gather some data and tune the model parameters. But doing so requires extra time and labor. In this way, A/B testing seems to be a reasonable approach in evaluating models with different parameters. But similarly, this approach requires a classroom study and IRB approval, and also lots of efforts. Therefore, it might not be feasible to conduct multiple experiments, evaluate each model, and identify the most outperformed one. In our approach, we ran simulated experiments with the Everton's learner architecture, which is a framework for modeling human learning from demonstrations and feedback in digital environment. This framework supports a few different tutors with the goal of teaching different skills. The Everton's learner agents are simulated students generated by the AL framework. They utilize artificial intelligence and machine learning mechanisms to simulate human learning. For this study, we use the fraction arithmetic tutor. Here is the HTML interface for the AL agents, in other words, simulated students to interact with. This tutor provides 3 types of problems. First, adding fractions with different denominators, short as AD. Second, adding fractions with the same denominators, short as AS. And third, multiplying 2 fractions together, short as M. To explore different knowledge tracing approaches through simulation study, we implemented 6 knowledge tracing conditions. Random as a baseline model, the strict model, BKT model with default parameters, BKT model with human-based parameters, and BKT model with simulated parameters, and lastly, the DKT model with simulated parameters. We created 30 simulated students for each of the 6 conditions, providing 80 questions for each of the 3 question types, and analyzed the data generated. There are a total of 14 knowledge components in our analysis, 8 for type AD, 3 for type AS, and 3 for type M. Each KC for each problem constitutes a unique skill. After we ran the simulated experiments, we first look at the numbers of problems that were administered by the tutoring system in each condition. The random tutor always takes all the problems for each type. The strict tutor takes less problems than the random tutor, but more problems than the BKT tutors. The 3 BKT tutors take similar numbers of questions in each type, and the DKT tutor almost takes all the questions in add different, but only less than 3 questions in add same and multiplication. To get a better sense of the overall differences between the random, strict, BKT random, and DKT conditions, we then use the addictive factor model, AFM, to examine the learning curves. Here we plotted the overall learning curves for the data from these tutors. This figure shows that the BKT tutor stops giving practice earlier than the strict tutor, which subsequently stops giving practice earlier than the random tutor and the DKT tutor. Then we want to look at the probability that students will get each skill correct at the point where the model assumes they have reached mastery. This figure shows the average predicted correctness across students after the final practice opportunity for each skill. We can see that for most KCs, the prediction is higher than 95%, which in turn suggests that the students have obtained mastery in these KCs. Unfortunately, the KC, AD answer denominator, which refers to computing the answer denominator in add different problems, has the lowest overall next step correctness prediction in all of the 6 conditions. Furthermore, to better evaluate how well each knowledge tracing approach handles the trade-off between maximizing students' performance at the end of training while minimizing the amount of practice they receive, we computed a metric that we call efficiency. To compute this efficiency score, we divided the predicted correctness at the end of training by the number of opportunities that the students received for each student and each KC. We then averaged over students to get an efficiency score for each KC. Finally, we averaged over KCs within each problem type, AD, AS, and M. This table demonstrates 3 model efficiency scores for each of the 6 models. The bigger the value, the more efficient the model is. The model efficiency score complements accuracy and provides more information for use in selecting the best knowledge tracing approach. Although the random model gives the highest correctness prediction, It is the least efficient one as it administers all the problems during the training process. The BKT random model appears to have lower predictions than the strict model in previous figure. However, the model efficiency suggests that it is more efficient than the strict model. To validate the feasibility of generating BKT parameters using simulated student data, we did a correlation analysis of the random-based BKT parameters and human-based BKT parameters. This figure shows that there is a positive correlation of around 0.65 in the learn parameter, which means the simulated students generated by apprentice learner have a similar learning rate as the human students, indicating that our simulated students' approach of obtaining model parameters is feasible. Lastly, we take a closer look at the estimates of several knowledge tracing approaches for different sequences. This figure shows a comparison of the predicted correctness at each problem-solving step among the BKT model with random-based parameters, the strict model, and the DKT model on the AD answer denominator knowledge component for a single student. Both the BKT model and the strict model provide consistent prediction over time, while the DKT model's predictions tend to jump around, but generally do not seem to be increasing despite getting the problem correct multiple times in a row. Upon further investigation, we found that the DKT model tends to use predictions to decide which cases are mastered, so it can pick another problem. Unfortunately, for multi-step problems, some cases cannot be correctly answered on the first step of next problem because there's an order of using the skills to solve the problem. This results in a side effect of confusing the mastery learning system into thinking that the KC is unmastered. Because previous work by Peach and others only look at the problems that had a single step, so this issue never occurred. To summarize, our results prove that simulated students can successfully test online knowledge tracing approaches. The strict model works well for mastery learning and has reasonable efficiency, though it seems that this model is giving a bit more practice than strictly necessary. The BKT models also work well for mastery learning and generally seems to have the best efficiency of the approaches we compared. Multiple studies suggest that the DKT model has good predictive performance for offline predictions, but we found that it does not seem to work properly for online knowledge tracing, particularly in cases where problems have multiple steps. We also find that it is feasible to initialize BKT parameters for intelligent tutors using simulated student data as an approach of testing multiple models before technically deploy a tutoring system. We have a few numbers of additional future directions we would like to explore. Firstly, we intend to individualize the apprentice learner models to make it better mimic the behaviors of different kinds of learners. For example, high-performing students and low-performing students, students with different motivation in learning, and those who suffer from learning disabilities. Second, we would like to explore ways of outputting skill dependency models from AL agents to better study the problem-solving sequence and identifying which skills should be practiced before others. Third, as our analysis shows that the strict model is a simple but promising model that may achieve high learning efficiency, it would be interesting to play with the number of cracks in a row as a mastery threshold. Fourth, we will try to apply fix to the DKT model and address the concerns we have identified and enable its use in online mastery learning. Last but not least, we would move beyond simulation and extend to a human experiment to explore how well our simulated students predict which knowledge tracing approaches will yield the best learning for human students. That is all for this presentation. Please feel free to reach out to us if you have questions or thoughts. Thanks for your time.